We're going to take a look at geometric sequences. And the learning goals are to connect geometric sequences to exponential functions, use arithmetic and geometric sequences in series to model real-world situations. And you'll know you have done this by being able to identify common ratios and find specified terms for geometric sequences, and also write the recursive and explicit definitions for the nth term in a geometric sequence. We're going to start off with a scenario where we have a business that is thriving, where more and more customers are trying out products, and as a result they're increasing the sales. The company made $20,000 in revenue their first month, and then the next month it grows by 3%, and it continues that 3% growth every month. In the table, we see month 1 has a revenue of $20,000, and month 2 has a revenue of $20,600. That we can see that it grew $600. And that $600 most students can recognize comes from the multiplication of 20,000 multiplied with 0.03. We'll see in the next month that it doesn't grow exactly by 600. That's because this is not arithmetic, it's geometric. Now the growth, instead of 20,000 times 3%, would be 20,600 times 3%. And that is going to give $618. So we can see this, the amount growing every month is not the same. And we could keep doing that with a lot of steps of multiply by 3 and then add that to the original. Multiply by 0.03 and add to the original. However, that's really time consuming if I'm wanting to know a month that's a long ways out. So we want to come up with a pattern. And that pattern is to recognize that we have a 3% growth, and that we're maintaining the original amount. We're maintaining the original, which is 100% of the revenue. So 3% growth plus 100% of what original revenue was creates 103%, or as a decimal, 1.03. This is going to be our common ratio. It is growing by 3% every time, so our ratio is 1.03. That means I could have taken 20,000 and multiplied it by 1.03 to get the 20,600. And for the third month, I could take 20,000 and times it by 1.03 squared, since it's grown for 2 months. First month is 20,000, then we grow 3%, then we grow 3%. And for month 4, it's 20,000 multiplied with 1.03 to the 4th power. In case you're not sure where your power button is on your calculator, it is your caret button right there. So I would type in 20,000 and multiply it by 1.03 to the 3rd power to get the 4th year. And I can see on my paper I should have had a power of 3. And that will give me $21,855. To reinforce the fact that this is not growing the same amount, I would like you to record the answer to this question. No, the growth of 3% is different each month, as 3% is multiplied with the prior amount. Which is always changing. Number 3, write the recursive form to figure out the new month's revenue if you know the previous month's revenue. So recursive allows us to go from a prior term, t sub n minus 1, and multiply it by that common ratio. In this case, it would be t sub n equals t sub n minus 1, the month right before, multiplied with 1.03, our common ratio. If we want to predict, sorry, I should have moved that. If we want to predict the company's revenue in month 11, we would probably want to use the explicit form as a faster track. And that explicit form is what we have really up in the table. T sub n is going to equal your very first month's revenue multiplied with the common ratio raised to the n minus 1 power. If I have 11 months, this would be 20,000 multiplied with 1.03 to the 10th power, because of 11 minus 1. Using our calculator, I get a revenue that is about $26,878. And if we were to use our table of values and put in our total amounts in months 2, 3, and 4, not ideal here, but this is what it looks like, we would have an exponential. And I'm going to go ahead and erase those lines because we can't have partial months. So we should just have those points on there with no line through them. And this shape is exponential. Any geometric function will have a common ratio, r, and it turns into an exponential. Let's flip this over for the next problem. Suppose that after many months the company's revenue starts decreasing by 3%. How would this affect your calculations? Well, instead of growing, we have a decay or a decrease of 3%. And what that means is instead of 100 plus 3%, we're going to have 100 minus 3%. And so our common ratio is going to be 0.97. Our explicit form would be t sub n equals whatever amount it is at the time. I'm going to say 20,000 just to have a number, multiplied with our common ratio raised to the n minus 1 power. Still working with the information from before, we're going to write the domain of this company's revenue. Domain has to do with x values, also known as input. And range has to do with y values, which has to do with our output. So the input are the x values of month 1, 2, 3, and so on. And the output is the revenue, so 20,000, don't put any commas, so that way you can see it's 20,000. Then a comma for the next term or the next month, which was 20,600, and the next month, which was 21,218, if I have that number right. Dot, 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 squiggle brackets. Okay. So domain x values, range y values. Read the problem out loud and try to come up with an equation that will help you fill out this table. So the rate that we're working with has 100%. However, it says that it's less than 30% every single night. So when you subtract that, you're going to get a 70%, and that means your common ratio, your base in your work, is 0.7. When it comes to the recursive definition, your recursive should be that you're taking the term right before and multiplying it by the 0.7. You are welcome to write it with the parentheses or with just a dot. When it comes to the explicit definition, that's when we're going to write it with the power involved. So your very first term multiplied with that common ratio to the n minus 1 power. In this problem, it would be 3,500 as our first term, multiplied with 0.7 to the n minus 1. I want to predict for the 10th night, so I'm just going to change all my n's to 10. And I'm going to find out that on the 10th night, there's not a lot of money made, which is only $141.24. So I wouldn't keep that show up. On letter C, the wording gets a lot of people. This one says, if the performance's revenue is better than anticipated and each night after the first night is 80% of the previous night's revenue, what is the explicit definition? Now, something that's really helpful in here is it says its revenue is better than anticipated. So before our base was 0.7, and if we want it to be better, it needs to be higher than 0.7. They're telling us that that base is going to be a 0.8 because you're keeping 80% of it. And so your explicit definition still has the 3,500, but your base is 0.8. And when you do that formula for the 10th night, you should have more money than you did with the 70% rate. And on my calculator, I had $469.76.